This session will be dedicated to crownfires, the likelihood that they happen, crowning or not crowning, uh, their relative probabilities, how fires will go from passive crown fires to active crown fires, and in the case that there is an active crown fire, what would be the likely rate of spread. So different models are present in this spreadsheet, and because of that you have different sections in the same spreadsheet. So the inputs are basically fire line intensity of the surface fire, foliar moisture content, canopy base height. With those three, we can have we can use the model by Van Wagner. We can compute a critical fire line intensity, and we have an indication if it's going to be a crown fire or not. So with these kind of intensities and film foliar moisture content and canopy base height, the indication is that it's not going to be a crown fire. But of course, then we can change this to from 3000 to 10,000 and see what happens. And then when you go from 3000 to 10,000, the output is already a crowning fire. It goes over, it's more than the critical fire line intensity, and then it will have a crown fire. Will have a crown fire. If you go back to 3000 kilowatts per meter of intensity, we say that's not won't be a crown fire. But of course, if you decrease your canopy base height from 8 meters to 3, so again, you have already a crown fire because your canopy base height is relatively low, and then a crown fire is going to develop uh, more easily. So you can also include slope steepness and flame plume angle and air temperature, and with these you can use the model by Alexander, which looks at the temperature at the base of the canopy, and it looks at the critical temperature for ignition, 673, and if the temperature at the base of the canopy is higher than this one and the critical temperature, then the prediction is that crowding will occur. So with these conditions, this model by Alexander will also predict crowding. And of course, you can look and see what are the difference with air temperature, if it makes a difference or not. So if you go from 300 to 280K, it doesn't make a difference. It will still crown to be a crown fire if you have this canopy base height. But of course, if you have a higher canopy base height, 10 meters, then the predictions of both is that it's not going to be a crown fire. So you have two different systems that are somehow related, but they are both uh, predicting that in this case crowning will not happen. So the other approach, the other similar approach, is done by Xantopoulos and Wakimoto that are looking at a comparison between the residence time of the fire and the time to ignition for different species. So time to ignition with these characteristics of temperature um, are for ponderosa pine 85 seconds, 150 seconds for lodgepole pine, and it will be 224 for Douglas fir. And so what happens here is that we have to provide an estimate of the residence time. Of course, residence time can be estimated by surface area to volume ratio for the diameter of the particles, so you can provide this kind of information, data, in, as an input. So if you say it's 100 seconds, if it's 100 seconds, this is already above the critical time to ignition for Ponderosa Pine, so it will predict with these conditions, foliar moisture content and air temperature, that Ponderosa Pine will ignite, but lodgepole pine and Douglas fir will not ignite. So for this residence time. So these are three different approaches that can be used, and they are very useful in terms of comparison with each other. Then we'll have the, some empirical equations that were derived by Cruz and others, where they estimate a probability of crowning. So here what they have is just the idea of if it's going to be a crown fire or not. Here Cruz assigns the probability of crowning. And the probability of crowning is dependent on wind speed at 10-meter height, surface fuel consumption, fine fuel moisture content. So in this case, it's predicted that it's going to have a crown fire, but if you increase the fuel moisture content to 100%, for instance, so the probability of crowning will be 0, and if you go for 30% moisture content, the probability of crowning will be will be close to 1. So here you see, let's say, a given probability, estimated probability, according with the previous information. And here you also see that this probability of crowning, that is used also as a torching index in some systems like in Nexus, that how that changes with wind speed. Of course, higher wind speeds will increase the probability of crowning. So here you have the wind speed at 10 meters, 50 kilometers per hour. If you reduce it to 5 kilometers per hour, you have already non-crowning. So you are in this area of the graph when before you were there, very close to 100% probability that crown would occur. So you can also play a little bit with this data and understand how they affect crowning probability. Then the next question is, if crowning occurs, what would be the spread rate? And then you have three different systems of calculating the spread rate. In this first one, Van Wagner just indicates if there is if we'll have active crown fire or not. So this is the canopy bulk density, the critical mass flow rate, and then here you can change this and compare it with the critical spread rate and see how if crowning is going to occur or not. If that is the case, then you'll get these two possibilities to look at the crown fire spread rate. And these are those provided by Cruz, based on the same type of information as before. So in this one, the prediction is that it's a very slow rate of spread, and this rate of spread is not an active crown fire, it's a passive crown fire. So we can have very slow movement of crown fires, so they are considered not to be active because it's basically dependent on what is happening in the understory. On the other hand, if you have this surface rate of spread is relatively important, and if the intensity is high, then you can have active crown fires, and with that you can predict the final rate of spread, which is a combination of the surface rate of spread with the rate of spread that is predicted by the models for the spread rate in the crowns. So, and the concept of the crown fraction burn is a measure of the transition between a surface fire and a typical crown fire. So here also you have the wind speed for these same conditions. What is the effect of wind speed on the predicted crown fire spread? And this is the critical spread rate. So in this case, with this 5 km/h wind speed, it will never reach the critical spread rate that will allow the fires to spread through the ground. So this is a little bit more complex spreadsheet because it has different aspects of crown fires. Here you are looking at crown fire initiation, if there is crown fire or not. Here you are looking for if the crown fire is active or not active, and if it's active, what is the spread rate that you would be that you would be estimating. Of course, in this case, for instance, you can change. You have to provide an estimate for the surface rate of spread for the surface fuels, and it's with this one that Rothermel computes the ground fire rate of spread. So it's a little bit more complex, but hopefully it will provide you some information on what are the limitations and the possibilities of using the different types of models.